Alright, got another video here for you. This is differentiation of logarithmic and exponential functions. Alright, let's get started. So, let's look at the derivative of natural log. So, the derivative, let's look at this one first. The derivative of natural log of x is just 1 over x. Okay? Just remember that. And then if we have the derivative of natural log u, where u is some function, something like this 2x cubed plus 1. That would represent the u. So to take the derivative of this, natural log u, it's just whatever you're taking the natural log of, that goes in the denominator, and the derivative of that goes in the numerator. And you can see this right here applies to this one also. So if we follow this rule for this one, for natural log x, well, what happens? X goes in the denominator, and then what's the derivative of x? 1. You get 1 over x. So let's get started and work some examples. All right. So here we have f prime of x is equal to, so whatever you're taking the natural log of, that goes in the denominator, and then the derivative of this goes in the numerator. So that's just 6x squared. And there's your answer. And yes, it's that easy. It's not bad at all, is it? All right, let's look at the next one. Well, what about this one? Well, for this one, what do we need to do? We need to use the product rule, right? Say we've got x times natural log x. So x would be our first function, natural log x would be our second function. So f prime of x is equal to the derivative of the first times the second plus the derivative of the second function, which is derivative of natural log x is 1 over x, times the first function. And so we would get f prime of x is equal to natural log x plus 1. The x's cancel. And there's your answer. So far, easy, right? All right, let's look at this one. Okay, so we could take the derivative of this. Well, of course, we're going to need to use the quotient rule. But let's look and see if maybe somehow we can simplify it a little bit, make it a little bit easier on us to take the derivative. So could we write this as natural log of x, of x to the 2/3 over x to the 4th, right? Because we have a property from algebra that says the nth root of a to the m is equal to a to the m over n, right? Going from radical form to exponential form. And then this would tell us that f of x is equal to 2/3 natural log x over x to the 4th, right? We also have a property from algebra that says the log of, base b, the log with base b of m to the n is equal to n times log of m with base b. We can take this exponent and bring it down in front. And then what I would like to do is let me change colors. And then I would like to do f of x is equal to 2/3 times natural log x over x to the 4th. So I want to take the derivative of this, and what I'm going to do is I'm going to take the derivative of this part, and then the 2/3 is just going to kind of tag along with it. Okay, we'll multiply the 2/3 at the end after I take the derivative of this in red here. All right, so I get f prime of x is equal to 2/3 times, now this is the quotient rule. So the quotient rule says the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator. And then this is all over the denominator squared. And so this is going to give me 2/3 times, and then that's going to be x cubed minus 4x cubed natural log x over x to the 8th. And so now I can put the let's do one step. I mean, if you do this step, that's fine. If you don't, that's fine too. But x cubed minus 4x cubed natural log x over 3x to the 8th. I'm doing this so you can see all the steps. I don't want to leave nothing out. And so what I'm going to do here is I'm going to write this 2x cubed times 1 minus 4 natural log x over 3x to the 8th. All I did is I factored out an x cubed. And then you can see that this and this cancel, and I'm left with x to the 5th. And so that's going to be 2 times 1 minus 4 natural log x over 3x to the 5th. And there's your answer. All right, moving right along. All right, let's look at this. Well, what do we have here? Here we have what? Chain rule. So we've got g prime of t is equal to 3/2 times t plus natural log t to the 1/2. Right, the 3/2 comes down. Subtract 1 from the exponent, times what? Times the derivative of what's inside the parentheses. So the derivative of t is 1, derivative of natural log t is 1 over t. And then, you know, I mean, how do you want to write this answer? I mean, there's not a whole lot more you can do with it. I guess if you wanted to, you could leave it like this, or you could write this as 3/2 plus 3 over 2t. So what I did is I distributed the 3/2 into here, and then I guess if you wanted to, you could write this square root of t plus natural log t, or you could leave it, or you could leave this as raised to the 1/2, you know. But there's an answer, okay? I'm sure your teacher would be happy if you got that. They might even be happy if you leave it like that. I don't know. Ask your teacher. All right. All right, so the problems that we're fixing to work, they're going to be some word problems. In this one, you can see they want us to find the equation of a tangent line. And basically what it is you're getting more practice finding derivatives. Okay? And you see this is just a different function. Finding the derivative is part of a problem. So you're getting more practice on finding derivatives of logarithms and exponentials. We'll do the exponentials in a minute. You're getting practice finding those derivatives, but they're within a word problem. Okay? All right. So we've got let's do this. F of x equals x minus natural log square root of x. Now, we can take the derivative like this, but remember we had a problem earlier. Let's make it easier. So let's rewrite f of x as x minus natural log x to the 1/2, which that's going to be f of x is equal to x minus 1/2 natural log x. Okay, get rid of those exponents like that. You know, this 1/2 exponent, get rid of it. Okay, it just makes it easier to take the derivative of the natural log. And so now I've got f prime of x is equal to 1 minus 1/2 times, and then the derivative of natural log x is 1 over x. So f prime x is 1 minus 1 over 2x. All right. Now, they want us to find the equation of the tangent line when x equal 1. So remember, to find the equation of the tangent line, what do you need? You need a point on the line and you need the slope. So let's find the slope and then we'll get the point. So the slope is just the derivative evaluated at the point, which is this x value, x equal 1, because see, we're just in terms of x. So that's going to be 1 minus 1 over 2 times 1, which is 1 minus 1/2, which is 1/2. So there's our slope. Now we need a point on the line. Well, we've got x equal 1. Well, what do you need for a point? You need an x coordinate and you need a y coordinate. So how do we find the y coordinate? Well, we take the 1, x equal 1, and plug it back into our original function. So that's f of 1 is 1 minus natural log square root of 1. Square root of 1 is 1. Natural log of 1 is 0. 1 minus 0 is 1. And so it's at the point 1, 1. And so now we're going to use y minus y1 equals m times x minus x1. And at this point in the class, you've already worked a bunch of these problems. You should know how to do them. You should know how to work this. The only difference is when we're taking the derivative, we're taking the derivative that has a natural log in it, of a function that has a natural log in it. That's the only difference. And so now we've got y minus 1 equals 1/2 times x minus 1. And so y minus 1 equals 1/2 x minus 1/2. And then we add 1, so we get y equals 1/2 x plus 1/2. And there's your answer. All right. Moving right along. Here we go. It says a manufacturer determines that X units of a particular luxury item will be sold when the price, P of X, is 12 minus X times natural log X cubed, $100 per unit. Find the revenue and marginal revenue functions. Okay. All right, so the revenue, let's look at part A and then we'll look at part B. So remember the revenue, it's X units. So the revenue is equal to X, the number of units sold, times the price, which is P of X. So the revenue is equal to X times, where's our function? 112 minus X natural log X cubed. And so our revenue is equal to 112x minus x squared natural log X cubed. All right, so we've got to take the derivative of this thing. All right, so we've got r prime of x. Well, for one thing, it says what? Find the revenue and marginal revenue. So this would be your revenue. All right, now the marginal revenue, we take the derivative. Well, that's 112, that's the derivative of that, minus, now let's do this. Let's put this in a bracket. Minus the derivative of this. So this is product rule. So it's the derivative of the first times the second plus the derivative of the second. So x cubed goes in the denominator, derivative of that goes in the numerator, times the first function, x squared. Now, I know what you're saying. Well, you told us earlier to take this number here and throw it down in front. Right, to write this as 3 natural log x. And that is perfectly fine if you do that. But look, why did I not do that? Well, because look, when it's an integer like that, yeah, you can throw the integer down in front, but you really don't have to, because this is not difficult to simplify. Okay, but if you want to throw the 3 down in front like we did this, throwing the 1/2 down in front, then that's fine. I typically just take this exponent, throw it down in front like this if it's a fraction. Okay, if it's a fraction or just, whatever. But if it's an integer, I just leave it up there, because this is actually, this is easy to simplify. And so now I get r prime of x is equal to 112 minus 2x natural log x cubed plus, and now let's start canceling things out. So this x squared and this x cubed cancel. I'm left with x to the first. And then this x to the first and this x squared cancel, and I'm left with x to the first. So that's going to be plus 3x. And so now I get r prime of x is equal to 112 minus 2x natural log x cubed plus 3x. All right, so this would be our marginal revenue. Okay. All right, so that's part A. Part B says use marginal analysis to estimate the revenue obtained from producing the 5th unit. What is the actual revenue obtained from producing the 5th unit? So this goes back to a previous lesson. So we want to use marginal analysis to estimate the revenue obtained from producing the 5th unit. So for that one, that means we're going to take the derivative and evaluate it. Remember, you evaluated at 1 less, at the 4. And so that's going to be 112 minus 2 times 4. And I messed up. This plus here, I distribute the negative. That should be a minus 3x. My bad. Minus 2 times 4 times natural log of 2 cubed. No, I'm sorry, not 2 cubed. 4 cubed minus 3 times 4. And that is going to give us an answer of 66.73. Okay. All right. Now, well, and I guess here, look, that's 66.73, and remember the revenue is in $100 per unit. So this would actually be 6,000. Let's see, $6,673. Because that represents 66.7300, so we move the decimal 2 places to the right. And then we want the actual revenue obtained, so that's just R of 5 minus R of 4. And so we're going to plug 5 into the original and 4 into the original. So to do that, let me grab this and move it down so we can see it. All right, so that's going to be 112 times 5 minus 5 squared times natural log 5 cubed minus the R of 4. Make sure the R, when you plug the 4 in, you put all that in brackets because it's minus the whole thing. 112 times 4 minus 4 squared times natural log 4 cubed. And that gives us 57.83, which is $5,783. All right. And so there's your answer. All right. So all of this problem here, you've done it before. You've worked this before. The only thing that you didn't know how to do was find the derivative of a function with a logarithm in it. Okay. All right, now let's look at derivative of exponential functions. So let's look at the derivative of e to the x. Well, derivative of e to the x is just e to the x. Okay. Then if you have the derivative of e to some function, like for instance this one, see the x squared plus 1, then your derivative of e to the u is just e to the u and then times the derivative of your exponent. And you can see if you apply this to this, you'll get e to the x. So the derivative of e to the x is e to the x, and then what's the derivative of x? It's just 1. 1 times e to the x is e to the x. Okay, so let's do some examples here. So we've got f prime of x is equal to e to the x squared plus 1 times the derivative of your exponent, which is 2x. And so we get f prime of x is 2x e to the x squared plus 1. And I like to write, like whatever you have here, I like to write it in front. All right, well, let's look at the next problem. I didn't leave myself a whole lot of room on that problem, did I? All right, so let's look at this one. So this one is what? This is quotient rule. So we have f prime of x is equal to the derivative of the numerator. So that's e to the negative 3x times negative 3. So e to the negative 3x is e to the negative 3x times the derivative of your exponent times the denominator. So this is the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator, and then all that over the denominator squared. And so here, let's put an extra step in here. To x e to the negative 3x, all that over x squared plus 1 squared. All right, so now what I like to do here is I like to factor out that common factor of e to the negative 3x. See, I'm factoring this out, and I'm factoring this out. And so that's going to leave me with negative 3 times x squared plus 1 minus 2x over x squared plus 1 squared. And so that's e to the negative 3x times negative 3x squared minus 3 minus 2x over x squared plus 1 squared. And so we can write this e to the negative 3x times negative 3x squared minus 2x minus 3 over x squared plus 1 squared. All right, I just wrote this part in descending powers. That's all I did. And so this would be your answer. All right, let's continue on. Okay, find the largest and smallest values of the function f of x equals x e to the 2x on the interval where x is between negative 1 and 1. So you've done this before too, absolute, max, and min. Okay, you got to find your critical numbers, and then you evaluate the original function at the critical number and the endpoints of the interval, and then you see which one's the largest, which one's the smallest. The smallest value is the absolute minimum, the largest value is the absolute maximum. And like I said before, the only difference is you just didn't know how to find the derivative of e raised to a power. That's the only difference, is this term right here. The procedure is the same that we did earlier. All right. So we've got f prime of x is equal to, and we got to use the product rule here. So it's the derivative of the first function times the second function plus the derivative of the second function. So derivative of e to the 2x is e to the 2x. Now let me show you something here. So derivative of e to the 2x is e to the 2x times the derivative of the exponent. What's the derivative of the exponent? It's 2. And you can just write the 2 in front. You don't have to write it behind. It doesn't matter. Okay, so there's your derivative. So what I'm going to do here is I'm going to factor out this common factor of e to the 2x. So f prime of x is equal to e to the 2x times 1 plus 2x. And so now we set this equal to 0. E to the 2x times 1 plus 2x equals 0. And so we've got 1 plus 2x equals 0. 2x equals negative 1, x is equal to negative 1/2. Now, you might be saying, well, why did you just set the 1 plus 2x equal to 0? How come you didn't set this e to the 2x equal to 0? Because it's never going to be 0. Tell me a number you can plug into x to make this e to the 2x 0. You can't. It's always, this e to the 2x, it's always positive. It's never going to be 0 and it's never going to be negative. So we don't have to even worry about that term. All we have to do is set this one equal to 0. And so now we're going to take our original function. We're going to take the original function and we're going to evaluate it at negative 1, negative 1/2, and 1, right? We take the negative 1, the 1, and the negative 1/2 and we plug it into that, into the original function. And when you do that, you get negative 0.136, negative 0.184, and 7.389. And so it's just asking us for the largest and smallest values. So you can see our smallest value is at x equal negative 1/2, which is the negative 0.184, and our largest value is at x equal 1. See, it's 7.389. And there you go. All right, moving right along. All right, so here we've got exponential and exponential growth and decay. This is a little something. This is a little bit different here. So let's just take a look at this. It says if q of x is equal to q naught e to the kt, then q prime of x equals k times q of x. And q of x changes at the percentage rate 100 times k. Okay, so this tells you how q of x changes at this k value, or the rate of change is the k value, and if you want to put it as a percentage, you got to multiply that k value by 100. Okay. All right, so it says a demographer studying a certain community uses an exponential model, and it tells us p of t is equal to p naught e to the kt for the population where t is the number of years after 1990. If the population is 100,000 in 1990 and 145,000 in 2003, at what annual percentage rate is the population increasing? All right, so there's a couple of things. This, I don't know, you may have had this, you may not have. You should have had something similar to this. This just kind of goes back to like if you took finite math, you know, something like that. All right, so it says the population is 100,000 in 1990. So what that's telling us is that P of 0 is equal to 100,000, right? Because what does it say? It says for the population where T is the number of years after 1990. So that's your initial year. That's the year T equals 0. And then so what that's saying is if I plug 0 in for T, I should get 100,000 as an answer. okay? Because P of t represents the population. So if you plug 0 in, you should get 100,000 as an answer. And then for this one, 145,000 in 2003. Well, 2003 is what? 13 years after 1990. So if I plug 13 in for t, I should get 145,000 as an answer. So basically it's saying at what annual percentage rate is the population increasing? So we need to find k. All right, so let's figure out what P naught is. Well, it's telling me that P of 0 is P naught times e to the k times 0, and that should equal 100,000. So look at this. Do you agree that e to the k times 0 is e to the 0? Right? So look, if we take P naught e to the 0 equals 100,000. So what does that mean? E to the 0 is 1. So that's telling us that P naught is 100,000. So now I have P of t equals 100,000 e to the kt. So I figured out what P naught is based on the initial population at the year t equals 0. All right, now this right here, this P of 13, it's telling me that if I plug 13 in for t, so that would be 13 in for t, 13 times k is 13k, right? I just replaced the t with the 13, and I just wrote the 13 first. That should equal 145,000. All right, so now you can see this equation here I have. I can actually solve for k. K is my only variable. And so I've got 100,000 e to the 13k equals 145,000. And so e to the 13k equals, so I'm going to divide both sides by 100,000, and that gives me 1.45. Okay, so all I did there, let's undo that. I'm going to divide both sides by 100,000. All right. And so now to solve this, well, remember, you can just take the natural log of both sides. And so now I have 13k equals natural log 1.45. Don't panic. I'm going to explain where the 13k comes from. Okay? All right. So if you remember back from algebra, see, you're in calculus now. You're supposed to know all that stuff from algebra. If you have the log of b to the x with base b, that is equal to x. In other words, if the base of your exponent and the base of the log are the same, your answer is your exponent. Okay? And also remember that the natural log of, I don't know, whatever, say the natural log of x, that is equal to the log of x, with base e. So if it's natural log, it's understood to be base e. So what do I have here? I've got natural log e to the 13k. And so remember, natural log is the same thing as log base e. And you see how the base of your exponent and the base of the log are the same? So that means your answer is just your exponent. Okay, and of course, you don't show all of this work. You just picture natural log is log base e. So that e and that e are the same, so your answer is your exponent. But I just wanted to show it out like that so you could actually see it. And so now we get k is equal to the natural log of 1.45 over 13. And so this is equal to 0.0286. And they want to know the percentage of increase. So we have 100 times 0.0286, which is equal to 2.86%. All right. There was no calculus involved in that, right? We didn't even have to take a derivative to work that problem. All right. Now, let's look at this problem. This is a nice, long, nasty problem. Let's see what we've got here. All right. It says a manufacturer determines that D of P equals 5,000 e to the negative 0.02 p units of a particular commodity will be demanded or sold when the price is p dollars per unit. So if you've watched any of my videos, this is the first optimization video. I've got 2 videos on optimization. Got optimization and then a more optimization. That's how this book does it. It splits it up into 2 it covers it over 2 sections. It's a lot of problems. Each one of the videos is over an hour long. So this elasticity of demand, revenue stuff, all that stuff is what we did before. Okay, you have done this. And like I've said, for what? Now the 1,001 time, it's exactly what you've done before. It's just the functions this one has an e to a power in it. You didn't know how to take the derivative of e to a power. Okay? All right, so find the elasticity of demand for this commodity and for what values of P is the demand elastic, inelastic, and of unit elasticity. All right, so let's look at part A. And let's go ahead and write I'm just going to write this down. D of P equals 5,000 e to the negative 0.02 p, and I'm going to go remember the D of P, you can write that as Q equals, that's 5,000. I went over that, the D of P and Q, we discussed that in that previous video, e to the negative 0.02 p. All right, and so remember, your elasticity of demand is what? Is the elasticity of demand is P over Q times dQ dP. That's your formula for it. Okay, so we need the derivative of Q. So the derivative of Q with respect to P is equal to 5,000 e to the negative 0.02 p times the derivative of your exponent, negative 0.02. All right, now that's going to give us E of P is equal to P over Q. Well, what's Q? Q is 5,000 e to the negative 0.02 p times 5,000 e to the negative 0.02 p times negative 0.02. Now you might be wondering, well, why didn't you multiply that times the 5,000? Do you see it now? This and this cancel. And so we are left with E of P is equal to negative 0.02 p. And there you go. There's your elasticity of demand. All right, now we want to know, where is it of unit elasticity, elastic, and inelastic? Well, remember, that goes back to, and I'm going to do this up here to kind of save some room. So, well, no, I guess I better do it down here. If I need more room, I'll just have to erase some stuff, which I think I'm not going to have enough room to work this whole problem. So we may go back up top and erase some of this. All right, so we've got the absolute value of E of P is equal to 0.02 p, right? Absolute value is positive. All right. So we know this is unit elasticity when what? When the absolute value of E of P, which, what does that equal? That's equal to 0.02 P. When is it unit elasticity? Well, it's when it equals 1, right? Which that gives us, if I divide both sides by 0.02, I get P equals 50. And it is elastic when the absolute value E of P, which is 0.02 P, when it is what? When it is greater than 50, which means P, when it is greater than, I went ahead and solved it, when it's greater than 1. So that means P is not equal. So that's when P is greater than 50. And then it's inelastic when absolute value E of P, which that's equal to 0.02 P, when that's less than 1. So that means if I solve for P, P is less than 50. And so this is what they're wanting to know there. When is it unit elasticity, elastic, and inelastic? All right, so now let's go to part B. It says, if the price is increased by 3% from $40, what is the expected effect on demand? All right, so let's see what the elasticity of demand is at, we'll need to see what the elasticity of demand is at 40. But let's go ahead and calculate. This is part B, and we know Q is equal to, 5,000 e to the negative 0.02 P. Okay, that's our function, and we want to know when P is equal to 40. So we have Q of 40 is equal to 5,000 e to the negative 0.02 times 40. So if you punch that into your calculator, you're going to get approximately, this is a rounded number, 2,247 units. I've already got these values calculated. And the elasticity of demand is E of 40, which is equal to what? Well, what's my elasticity of demand? Well, we calculated it right here. That's, remember, that's E of P is equal to negative 0.02 P. See, that's what we found right here. All right, so that's going to be negative 0.02 times 40, which is negative 0.8. Okay, so what this is saying is that a 1% increase, remember what this means in price? Results in a decrease in the quantity demanded by approximately 0.8%. Okay, so a 1% increase in price will give us a 0.8% decrease in demand. That's because we got the negative 0.8 here. Okay. So what it's asking is, if the price is increased by 3% from $40, so the 3% from $40. So that's what that gives us, the P of 40. And we calculated for a 1% increase. So an increase of 3% in price from $40 to, now what's 3% of 40? So if you take 40 times 0.03, you get 1.2. 1.2 plus 40 would give us $41.20. Okay, and this results in a decrease in demand of approximately, now how do we find that? Well, that's going to be 2,247. That's what the units we had at when it was 40. And then that's going to be times 3 times the 0.008. So that's the 8% decrease in demand, 8% decrease in demand at 1%, but we're doing 3%. So if that's 1%, 3 times 1 would give us the 3. So we're going to multiply this by 3, and that would give us 54 units. Okay, that would be the decrease in demand of approximately 54 units. So that would go from 2,247 to, and then it's the 2,247 minus 54. That would go to 2,193 units. And there you go. And see, we're right here already, and we've still got part C. So I'm going to go back up top and erase all this stuff and work part C. Okay. All right, so now we've got part C. I paused it while I erased it. So for part C, well, first let's write down our function Q is equal to 5,000 e to the negative 0.02 p. Okay, that's what they give us in the problem. All right, so find the revenue obtained by selling Q equals D of P units at P dollars per unit, and for what values of P is the revenue maximized. All right. So remember, the revenue, we'll call that RP, is equal to, all right, it's the number sold, okay, times the price per unit, which is P. So this represents the number sold, this represents the price. Isn't that revenue? The price times the number sold. So that's actually just P times Q. And so we get R of P. We get R of P is equal to P times 5,000 e to the negative 0.02 p. So R of P is equal to 5,000 P e to the negative 0.02 p. There's our revenue. Okay, it says find the revenue R of P. And so we've done that. There's your revenue. And then find for what values of P is the revenue maximized. Well, do we know how to do that? Of course we know how to do that. That's where you take the derivative and find the critical numbers, right? All right, so let's find the derivative of this. So this is product rule. So look, it's our first function and there's our second function. So remember, the derivative is the derivative of the first times the second plus the derivative of second times the first. So the derivative of the first is 5,000 times the second function, negative 0.02p, plus the derivative of the second function, e to the negative 0.02p, times the derivative of the exponent, times the 5,000. All right. And so we get r prime of p is equal to, so what I'm going to do, 5,000p. I forgot that p there. See, this right here, that's the derivative of this, and then times the first function. I just forgot to put the p on there. So what I'm going to do now is I'm going to factor out a 5,000 e to the negative 0.02p. I'm going to factor that out. So if I factor it out of here, I'm left with 1. Factor it out of here, I'm left with minus 0.02p. All right. All right, so now we've got to set this equal to 0. So I've got 5,000 e to the negative 0.02p times 1 minus 0.02p equals 0. So I've got 1 minus 0.02p equals 0. So that's negative 0.02p equals negative 1. So p is equal to 50. Okay, so that's what we're going to test. We're going to show that is a maximum. And now remember, once again, this part right here, that's never going to be 0. That exponential function will never equal 0. So we don't have to worry about setting it equal to 0. All right. So what we can do here is we can actually find the second derivative. Whoop. Come on and close. All right, so we've got r double prime of p. So we're going to take the derivative of this. So this is your first function. This is your second function. So it's product rule. So the derivative of the first, so that's 5,000 e to the negative 0.02p times the derivative of the exponent, all right, times the second function. All right. So it's the derivative of the first function, which is this, times the second function, plus the derivative of the second function, which is negative 0.02 times the first function. And that's going to be 5,000 e to the negative 0.02p. And so I get r double prime of p is equal to, so let's kind of let's multiply this out. That's going to be negative 100 e to the negative 0.02p times 1 minus 0.02p minus, and then when you multiply that, you get 100 e to the negative 0.02p. All right. So there's your second derivative. You could actually stop right there, because basically what we're going to do is we're going to take the 50 and plug it into the second derivative. But let's just go ahead and simplify it a little more, just to get some practice. So I get r double prime of p. I'm going to factor out, let's see, what do I want to factor out? I want to factor out a negative 100 e to the negative 0.02p. And if I take it out of this one, I'm left with 1 minus 0.02p. Take it out of this one, I'm left with minus 1. No. plus 1. If I factor out a negative, that's going to change that to a positive. And so I get r double prime of p is equal to, let's see, what do we have here? Negative 100 e to the negative 0.02 p times, and that's going to be 2 minus 0.02 p. All right, so that's a good exercise to do. Okay. And so now I've got r double prime of 50 is equal to negative 100 e to the negative 0.02 times 50 times 2 minus 0.02 times 50. And that is approximately, this is going to be rounded, negative 37, which is less than 0. So that means we have an absolute maximum at p equals 50. All right. There you have it. So that's using the second derivative test. That I talked about that a little bit earlier in an earlier video. So the second derivative test, if you take your critical numbers and you plug those into the second derivative, if you get a negative answer, that means you have a relative or an absolute or relative maximum. And if you get a positive, that means it's a minimum. Okay. You can go back and either look at one of the videos or go back in your book or just look up in your book second derivative test and it'll show you. All right. All right. So now let's find the derivative here. We're almost done. Okay. We got this and a couple more problems. They don't take long to do. All right, so let's look at this. So if you're taking notes and stuff, don't write this down, what I'm fixing to write. So for one thing, well, this part you can write down. So f of x is equal to x plus 1 to the 1/3 over 1 minus 3x to the 4th. I'm going to rewrite everything with exponents. Okay, and so if you're taking notes after you write that, just stop. Okay, and I'll tell you when to start writing again. So if we took the derivative of this, we would get f prime of x equals, I tell you what, let me write in this color, and as long as I'm writing in this color, don't copy it down. All right, so this is quotient rule. So this is 1/3 times x plus 1 to the negative 2/3 times 1 times 1 minus 3x to the 4th minus 4 times 1 minus 3x cubed times negative 3 times 1 times x plus 1 to the 1/3 over 1 minus 3x to the 4th. I don't think I messed up anywhere, but anyway, that's not the point. We're not going to work the problem like this. But you see what happens here. This is a nightmare. It's a nightmare to simplify. Okay? We don't want to simplify that thing. There must be an easier way. And there is. Okay? But this is what it would look like if you did the quotient rule on it. Oh, and I'm sorry, that would actually be squared. Sorry about that. All right, I just wanted you to see here how nasty that would be to try to do that. So what we're going to do here is we're going to do logarithmic differentiation on this thing. So what we're going to do is we're going to take the natural log of both sides. All right. Now, this is equal to natural log f of x, which is equal to the natural log x plus 1 to the 1/3 minus natural log 1 minus 3x to the 4th. Remember when you learned how to expand and condense logarithms in algebra? You remember that? And more than likely, I would say 99% of you hated it. But let me tell you, you're going to love it now because this is going to make your life a lot easier. Remember when you got natural log and you got division in here? That splits up using subtraction. Remember those? You can write these down if you want. The log of x times y with base b is log of x base b plus log of y base b, and the log of x over y with base b is log x with base b minus log y base b. Remember, multiplication splits up into addition, division splits up into subtraction. And then remember, we have that property that says we can pull those down in front. So we've got natural log of f of x is equal to 1/3 natural log x plus 1 minus 4 times natural log 1 minus 3x. Okay, and we may have to come up here. I'm running out of room. I didn't do too good leaving myself room on this. All right, so now we have, well, now we can take the derivative. So what's the derivative of natural log? Well, whatever you're taking the natural log of, that goes in the denominator, and the derivative of it goes in the numerator. And then this is going to be 1/3. What's the derivative of that? X plus 1. What's the derivative of x plus 1? 1. And then that's 4 times. And then we've got 1 minus 3x. What's the derivative of 1 minus 3x? Negative 3. And let's see. I'm going to take this instead of moving up. I'm going to take this and move it down. That part I'm moving down. That's the last thing we have to do. Let's go ahead and move it down some more. Make sure we have plenty of room here. All right. All right, so now I get f prime of x is equal to 1/3 times x plus 1 plus 12 over 1 minus 3x, right? And you might, well, do I distribute the 3? If you want to, you can. You don't have to. Just whatever floats your boat. If you want to distribute the 3, distribute the 3. I wouldn't. Whoop. That's f prime over f of x. I forgot to put the f of x down there. But what are we doing? We're trying to find f prime of x, right? So I've got f prime of x is equal to f of x times 1/3 times x plus 1 plus 12 over 1 minus 3x. And so we get f prime of x is equal to f of x. Well, what's f of x? There's f of x, right? Come on down. Come on. There we go. Come on. You're going to make it. My goodness. Come on. What happened there? I'm getting there. Be patient with me. There we go. So what's f of x? That's f of x. So that's x plus 1 to the 1/3 over 1 minus 3x to the 4th times 1/3 times x plus 1 plus 12 over 1 minus 3x. And there's your derivative. You see how much easier that was using logarithms and expanding them? Okay. I mean, there you go. A lot better than us going to have to try to simplify that other thing that I did at first. All right, so we've learned how to find derivatives of exponentials and logarithms. So, well, we learned how to find derivatives of e raised to a power, and we learned how to find derivatives of natural log. Well, what if the base is not e? What if it's not natural log? What if it's log with any base? Well, here's your formulas. So the derivative of b raised to the u, where b can be anything, it doesn't have to be e. Well, that's just b to the u times the natural log of the base times the derivative of the exponent. And then the log of u with base b is 1 over u, 1 over whatever you're taking the log of, and then times natural log of b, which is in the denominator, times the derivative of what you're taking the log of. So let's look at this. So we've got y prime is equal to, well, that's what, 2 to the x, right? 2 to the x times, let me write that better, 2 to the x times natural log of the base, so that's natural log 2, times the derivative of the exponent. Well, what's the derivative of x? It's 1. And so y prime is 2 to the x natural log 2. And then the last problem, this one, the derivative, that's going to be what? 1 over x natural log 3, right? 1 over whatever you're taking the log of, which in this case is x, times the natural log of the base. What's the base? It's 3, times what? Times the derivative of what you're taking the log of. Well, what's the derivative of x? It's 1. And so we get y prime is 1 over x natural log 3. And there's your answer to that one. And that is all of this video. I hope you enjoyed it. I hope you stayed awake for the whole thing. But check out my other videos. Give me a like, share, subscribe, comment. And I will see y'all in the next one. Later.